The Kuiper Belt is a region outside most of the planets of the solar system. Pluto was the first Kuiper Belt object discovered, and we didn't identify any more for about 60 years. On November 2, 2015, the world got its first glimpse at an object from the Kuiper Belt. It was one of the most unique photographs from space ever made public. However, that has just changed. The James Webb Space Telescope has captured the clearest image of the Kuiper Belt in history, and it's nothing like anyone expected it to be. The Kuiper Belt is located in the outer solar system and forms a cold, donut-shaped region. It lies beyond the orbit of Neptune, which is the 8th planet from the Sun. Initially, its shape was the most interesting thing about it, but it soon became clear that the Kuiper Belt was going to be one of the most fascinating features of our solar system. The belt is named after astronomer Gerard Kuiper, whose work in the mid-20th century laid the groundwork for understanding the region beyond Pluto. However, he wasn't the one who actually discovered it. In 1951, Kuiper published a scientific paper speculating about the existence of objects beyond Pluto, primarily focusing on the possibility of these objects without providing detailed predictions about their specific characteristics or arrangement. Pluto was initially considered the defining factor for the Kuiper Belt, but it's now understood that Neptune's orbit, rather than Pluto's, establishes the inner edge of the belt. The gravitational influence of Neptune has played a crucial role in shaping the dynamics of the Kuiper Belt. Although Kuiper's predictions were not directly aligned with later observations, his pioneering ideas and contributions were well known among astronomers. Over time, the general concept of the Kuiper Belt and its association with objects beyond Pluto became linked to Gerard Kuiper. In 1930, astronomer Clyde Tombaugh identified Pluto, marking it as the first object discovered in what we now know as the Kuiper Belt. During its discovery, the understanding of the outer solar system was limited, and astronomers did not anticipate a large population of icy worlds beyond Neptune. The prevailing view of the solar system included the inner rocky planets, the gas giants, and the outermost icy giant, Neptune. Pluto's identification, despite its elliptical and tilted orbit, led scientists to consider it a lone planet. It wasn't until 62 years later, in 1992, that the second Kuiper Belt object was discovered. This discovery made it clear that Pluto was not an isolated entity but part of a broader population of objects in the outer solar system. The subsequent discovery of numerous Kuiper Belt objects, KBOs, confirmed the existence of this region, which hosts a diverse collection of icy worlds beyond Neptune. Pluto's unique status in astronomical history lies in its initial classification as the 9th planet, a designation that persisted for several decades. However, as our understanding of the Kuiper Belt grew and with the discovery of additional KBOs, particularly those larger than Pluto, the International Astronomical Union redefined the criteria for planetary status in 2006. Pluto was then reclassified as a dwarf planet, although it remains one of the most important discoveries in our solar system. Without Pluto, we might never have explored the Kuiper Belt. This unique area is considered an extension of our solar system because it is part of the same cosmic neighborhood and is influenced by the gravitational forces of the Sun. While the 8 major planets, including Neptune, dominate the inner solar system, the Kuiper Belt extends the boundaries of the solar system into the outer reaches. It is distinct from the inner solar system, characterized by a collection of icy objects, including dwarf planets, asteroids, and comets. According to NASA, the material in the Kuiper Belt is believed to be remnants from the early solar system, dating back approximately 4.6 billion years, and is thought to have preserved conditions and materials from that time. This is like history unfolding before our eyes. Inside this belt, we have Pluto and its moons, as well as other dwarf planets such as Haumea, Makemake, and Eris. Not only that, but the Kuiper Belt is also home to a diverse population of smaller icy bodies. The Kuiper Belt is considerably larger than the main asteroid belt. The main asteroid belt is a collection of rocky objects primarily located between the orbits of Mars and Jupiter. It is relatively thin and contains many small to medium-sized bodies. On the other hand, the Kuiper Belt is a more extensive and distant region. The mass of the Kuiper Belt is estimated to be 20 to 100 times greater than that of the asteroid belt, indicating that it contains a more substantial amount of material, both in terms of the number of objects and their overall mass. This is part of the reason why it was so shocking that the discovery took so long. However, just because it took a while doesn't mean this place isn't important to the solar system. It is home to a diverse array of celestial bodies, including dwarf planets like Pluto, Haumea, and Eris. Pluto, discovered by Clyde Tombaugh in 1930, was once considered the ninth planet until the International Astronomical Union redefined planetary criteria in 2006, leading to its reclassification as a dwarf planet. Pluto, with a diameter of approximately 2,377 kilometers, orbits alongside other significant dwarf planets in the Kuiper Belt. Study into Pluto has also helped scientists and researchers understand this distant region better. This was just the start, though. Haumea, discovered in 2004 by a team led by Mike Brown, adds to the Kuiper Belt's diversity with its unique elongated shape, possibly a result of rapid rotation. This dwarf planet, approximately 1,960 kilometers in diameter, has provided valuable information about the intriguing characteristics of Kuiper Belt objects. Makemake, another discovery by Mike Brown's team in 2005, presents its own distinct features, with a diameter of around 1,430 kilometers. It lacks a significant atmosphere, yet its bright surface, composed of methane, ethane, and other materials, distinguishes it as one of the brightest objects in the Kuiper Belt. Eris, also discovered in 2005, is slightly smaller than Pluto but more massive, with a diameter of approximately 2,326 kilometers. Eris is a significant member of the Kuiper Belt, and its discovery contributed to the reevaluation of the definition of a planet, expanding our understanding of the variety and dynamics of objects within the Kuiper Belt. Together, these dwarf planets offer valuable insights into the composition and evolution of the Kuiper Belt and its role in the broader context of the solar system's history. Without them, we would be in the dark about this area. Many people around the world confuse the Kuiper Belt with the Oort cloud. However, the Kuiper Belt is more densely populated with objects and is thought to be a source of short-period comets, which have relatively shorter orbital periods. The Oort cloud, on the other hand, is an even more distant and spherical region that envelopes the entire solar system. It is believed to extend from about 2,000 astronomical units, AU, to possibly 200,000 Australian dollars from the Sun. The Oort cloud is composed of icy bodies often compared to dirty snowballs and is the hypothesized source of long-period comets, which have highly elliptical orbits that bring them closer to the Sun. The NICE model is a theoretical framework that suggests a series of significant orbital changes in the outer solar system, particularly involving the four giant planets: Jupiter, Saturn, Uranus, and Neptune. According to this model, the giant planets in the outer solar system did not always occupy their current orbits. Instead, they underwent a period of dynamic orbital evolution. The model proposes that interactions between these giant planets led to significant changes in their orbits. As a consequence of the shifting orbits of the giant planets, the NICE model suggests that a considerable amount of material in the Kuiper Belt, originally estimated to be 7 to 10 times the mass of Earth, could have been lost. Gravitational interactions and orbital changes of the giant planets may have caused Kuiper Belt material to be scattered, ejected from the solar system, or transferred to different regions. Today, the Kuiper Belt is in a state of slow erosion. Collisions between objects within the belt can produce fragments, leading to the generation of smaller Kuiper Belt objects. Some of these smaller objects may become comets, while others may not. The dust produced by collisions can be blown out of the solar system by the solar wind. The total mass of all material in the Kuiper Belt is estimated to be no more than about 10% of the mass of Earth. Although this may seem small, it is not insignificant. A significant number of Kuiper Belt objects have been discovered to have moons, smaller bodies that orbit around a larger primary object. This phenomenon is not limited to planets but extends to various objects in the Kuiper Belt. Along with the moons, some KBOs exist as binary systems. In a binary system, two objects of relatively similar size or mass orbit around a common center of mass, often referred to as their barycenter. These binary pairs can have a variety of orbital characteristics. Among them, some objects actually touch, creating a distinctive peanut shape. This configuration is known as a contact binary, where the two components are in physical contact with each other. However, this wasn't always public knowledge. NASA had to put in a lot of work to explore the Kuiper Belt. Pioneer 10 was one of the first spacecraft to approach it. Launched by NASA on March 2, 1972, Pioneer 10 embarked on what would become a mission lasting more than 3 decades. It was a groundbreaking spacecraft designed for the exploration of Jupiter and its surrounding environment, equipped with scientific instruments to study Jupiter's atmosphere, magnetic field, and radiation belts. Pioneer 10 made history as the first spacecraft to traverse the asteroid belt. In 1983, it achieved another milestone by becoming the first spacecraft to enter the Kuiper Belt region. Although Pioneer 10 entered this region, it did not specifically visit any icy worlds, as none had been discovered apart from Pluto at the time of its launch. The spacecraft's primary mission focused on Jupiter, and it transmitted valuable data about the gas giant back to Earth. Pioneer 10's trajectory and longevity allowed it to travel far beyond the orbits of the known planets, contributing to our understanding of the outer reaches of the solar system. Its journey past the Kuiper Belt laid the groundwork for future missions to explore this distant and intriguing region. Later missions, such as Voyager 2 and Cassini, significantly expanded our understanding of the outer solar system. Voyager 2's notable visit to Neptune's moon Triton in 1989 and Cassini's exploration of Saturn's moon Phoebe in 2004 provided valuable insights into these celestial bodies. Some of these moons are believed to have originated from the Kuiper Belt, having been captured by the gravitational influence of their respective planets. Most people are unaware that this is possible, but it is and has happened. This was just the beginning. There was much more information yet to be discovered in this region. The New Horizons spacecraft made history by conducting the first-ever flyby of Pluto in 2015. During its mission, New Horizons captured photos of a Kuiper Belt object known as 1994 JR1. This object, measuring 90 miles wide, was observed from a distance of 170 million miles, providing valuable data about the composition and characteristics of Kuiper Belt objects. In 2014, the Hubble Space Telescope made significant contributions by uncovering 3 KBOs that were considered potential targets for NASA's New Horizons Pluto mission. The telescope also detected 2 icy mini-worlds within the Kuiper Belt, located at the edge of the solar system. These findings prompted NASA to authorize a more extensive search for Kuiper Belt objects. The primary objective of this intensified search was to identify a suitable object for NASA's New Horizons spacecraft to observe up close after its flyby of Pluto. The 2 objects discovered during the search, currently called 1110113Y and 072009F, are located approximately 4 billion miles from Earth. Hubble's involvement in Kuiper Belt research dates back to 2003 when it captured 2 snapshots taken 12 hours apart of a Kuiper Belt object named 2000 FV53. This object, originally discovered from Hawaii in March 2000, played a crucial role in targeting Hubble's observations. The 3 newly discovered Kuiper Belt members identified by Hubble are exceptionally faint, up to 100 times dimmer than 2000 FV53. Their faintness renders them invisible to the human eye, necessitating the use of computer analysis by astronomers to locate them. Hubble's advanced camera for surveys tracked one of these objects on January 26, 2003, making it clear that something significant was being observed. However, it wasn't until the James Webb Space Telescope came into the picture that things became even more interesting. Its advanced capabilities opened up unprecedented opportunities for observation and analysis. The James Webb Space Telescope, JWST, is a state-of-the-art space observatory that excels in studying the cosmos, including regions like the Kuiper Belt. It uses infrared technology, as all objects with a temperature above absolute zero emit infrared radiation. The intensity and distribution of this radiation depend on the object's temperature. In the Kuiper Belt, where temperatures are extremely cold, the emitted infrared radiation is in the form of longer wavelengths, making it easier for this telescope to gather information. Different materials have unique spectral signatures in the infrared range. By observing an object in the Kuiper Belt using infrared light, scientists analyze the specific wavelengths of infrared radiation emitted or absorbed by the object. These spectral features provide information about the composition of the object. For example, water ice, methane, ammonia, and other molecules have distinctive infrared signatures, allowing scientists to determine the object's composition without relying on visible light observations. Infrared radiation can also penetrate through dust and gas more effectively than visible light, making it particularly beneficial for studying the surfaces and properties of Kuiper Belt objects. This is especially useful in dusty environments or thin atmospheres, as it reduces the impact of atmospheric interference and obscuration. This makes it particularly effective for observing the Kuiper Belt, where many objects are dim or distant. The large mirror also improves the telescope's resolution, allowing for sharper and more detailed images of Kuiper Belt objects, which is essential for obtaining clear data about these distant bodies.